Hello, everyone. So for those who don't know me, my name is Dr. Clement Chumesi. I'm a medical statistician for the Norfolk Department of Medicine at the University of Oxford. So for those who've not watched the previous video, this video is just a continuation of the previous video on cracking complex research problems using advanced regression, where we were diving deep a bit into forensic investigation based on empirical data. So if you've not watched the previous part or the previous video to this one, please kindly watch that before you progress with this so that you actually will be able to follow what we were doing. Thank you very much. I hope you enjoy it. Please, if not subscribed to the YouTube channel, kindly subscribe and share with your colleagues. Thank you very much. Cheers.
And just to, so the whole take-home message is that we just wanted to know how to use logistic regression for classification problem. And what you've learned, you can adopt it if the dependent variable was either dead or alive instances. So that is like a survivor data, or if the dependent variable was about whether an individual is infected or uninfected. Okay, and it's not just two categories. You can consider it when the categories are more than two. Just that in that case, you not use the GLM function. You use a certain function called multinom. That's for multinomial logistic. It's in R, and the package for that is called NNet. NNet is like it's a neural. It makes use of some neural network method. I mean procedure, but that's the best package for logistic, a multinomial logistic, and you can always go online and get that. You can always go to Google and type how to remember. Once you import data into R, everything else you can make use of Google. So for instance, you know how to import data. Now you want to do, let's say, a logistic regression. Imagine if you didn't know anything I've done today. You just go to how to do logistic regression. You get a lot of online blogs. People have done these things. Like for instance, this one, I can put it on my website. And once I put it on my website, you'll be able to, yeah. So if you want to send an email, once you go to Google, you type my name. Okay. Once you go to Google and you type my name, okay, I'm just doing it so that I don't have to necessarily send it to everyone. So once you go to Google and type my name, the first link you see here is my Oxford University website. If you click there, you see my email, either my Oxford email or my Gmail. Okay, and so you can send me the email via any of them. Just send me the email either via the Gmail or my Oxford email. Probably I'll say my Gmail if that makes it easier. But any of them, and then you'll be able to get access to. Yeah, so just go to Google, type my name, and yeah. So once you type my name, I think you get access to everything about me anyway. So everything, like everything. Yeah. So but the first link will take you to that. Okay, so without wasting time, I will end here, and don't forget to subscribe to the YouTube channel. The videos, everything we've done will be uploaded on your YouTube channel, and for the codes, we'll think about the best way for everyone to get it. But I'm sure I'll put it on my Piazza platform. This one, the Piazza platform, where you're able to access all these. But in order to be able to access this, I think once you send me the email for me to add you to the Piazza website, you'll be able to download everything. Okay. So without wasting time, I'll end here and I'll take questions. Thank you very much. Okay. So at this point, you can now ask questions. Yeah. Eric, go ahead.
Thank you so much for the opportunity, and I'm so grateful to be part of this particular training. I'm very excited and very enthusiastic about this delivery. But my question is quite simple. When we're doing the machine learning using the lasso, I realized that you're using the odds ratios to actually look at the magnitude of the coefficient to determine which one is relatively important. But I also know of this about the dominance analysis. I don't know if it's something that is.
Wait, before you continue, I'm just clarifying things. So when you do the lasso, what you see are not odds ratios.
Yeah,
What you see, no. When you do that, no. So for instance, don't forget that we first of all did the lasso regression, and after doing the lasso, it just took away those variables we should eliminate. and then the ones that had non-zero weights. So the lasso output are the weights. So the ones that have non-zero weight are the ones that we are considering as influential predictors to consider in fitting the logistic model. Okay, so we are using the lasso as a preliminary feature selection or variable selection technique to select the subset of variables that are more influential and free from multicollinearity. So the ones which have zero values are going to be taken away. And those variables, with those weights, we don't interpret them. They are just the weight of importance. Think of the lasso output as weight of importance. But after selecting the predictors and now using those selected predictors that lasso recommended in the logistic model, it is still a logistic model. In that case, it's not a lasso logistic model. The lasso logistic model was that when we were doing the feature selection, and whatever regression, whatever coefficient came were not the regression coefficient, but they were called the weight of the variable or weight of importance. Okay, so that those weight of importance basically we are not interested in interpreting them. So at the end of the day, we just selected the ones with the non-zero weight as the important or influential predictors to consider. And we now fitted the logistic regression again based on those subsets. And I just decided to add underscore lasso so that we know that these were the logistic model based on after we selected these predictors from the lasso feature selection. Does it make sense? Can you continue now?
Yeah, that's fine. So is it possible to do a dominant analysis so that you know the relative importance? I guess you also indicated that in R, it's possible for you to do the variable importance to actually.
Yeah. So that VIMP is not always something I would entreat or advise, because you can actually calculate the variable importance even without fitting a model. Okay, it means that if you pick a certain set of variables, let's say if you fit, let's say, a logistic model, and then you do that variable importance, I wouldn't want to use that variable importance as a measure of importance, because even those estimates you get, you can't interpret them. So but they would always agree with the size of the regression coefficient. Okay, so it meant that just use the size of the regression coefficient. Once the regression coefficient is higher in magnitude than a significant, then the highest the regression coefficient, the more important that variable is. And I think that should be the best statistical way of making that conclusion. The other ones are also alternative. Remember, there are always different methods. Even the feature selection, we said we can use rate, we can use elastic net. But at the end of the day, lasso is like, it applies like a brute force, which I think is better, because in that case, we are, at the end of the day, we are basically interested in which subset is the best, free from multicollinearity, and that will improve the model fit. And yeah, so I think stick to conclude on variable importance based on the size of the estimated regression coefficient, but not based on variable importance. Because think about it. If you fit machine learning, let's say you fitted a classification tree, gradient boosting machines, random forest, gradient, extreme learning machines, or maybe support vector machines. These are class of machine learning techniques. Each of them, the variable it will conclude as the most important will not be the same variable another model will conclude as important. So that's why I wouldn't want to use variable importance as a yardstick, even though at least it just says that anytime you are able to identify a certain variable from a particular model as significant, then if you do variable importance of that model, it should agree with what the model suggested here. So that, I think that's the take-home message. All right.
Thank you so
have I answered your question?
Yeah, I'm okay.
All right. Is it Eura? Yeah, go ahead.
Yeah, it's Sarah. Thank you for the presentation, quite detailed. So my question I already put in the chat is quite short. I'm asking, you said the training data it should be enough. And would you say 100 is enough to do this?
Okay. Yeah, I think the question is what is our quantitative definition of enough? All right. So apparently I think most literature suggests that a data set of 100, okay, is good enough for any analysis. But statistically, we believe that if a data size is 30 or more, we assume that that data set is large enough. That is it from classical hypothesis testing. We believe that once a data set is 30 or more, then it means it's large enough. But from a regression perspective, a data set over 100 is good enough. But think about it this way. It's just discretionary. I've done an analysis. Okay, so now let me share my screen once again, just to make us understand what I meant in a more practical sense. So let me share my screen. Okay, so now let me go to just a minute. Okay. All right. So just a minute. So I'm just using a certain paper. Okay, fine. Just a minute. Okay, so let's say this is like a paper, like a paper, one of my publications. Fine. So so here in this paper, the sample size, the truth is that the data, the sample size was 60. The entire data set was 60. And the reason why it's 60 is because we are looking at infections that are called rare infections. Rare infections means that when you take 2,000 people, only one person would have that infection. And that means that with such a data, if you want to do analysis on rare diseases or rare infection, naturally sample size will be low. But does it mean we shouldn't make any statistics on that? No, that's not what we are saying. So even though this was just 60, okay, for this analysis, we still ended up splitting the data set. Sorry. We still ended up splitting the data set into training and testing. So it meant for the 60, I ended up using 47 for the model fitting and 47 for the model fitting, and the remaining for what? The remaining for testing, right? So in this case, it still gave me an accuracy of, what was the accuracy? The accuracy was 80%, even with that. So I'm just trying to say that naturally, if your date, so this one was 60, but I still went ahead and did the splitting. Okay. All right. So it's just to say that the reason why the splitting is important is it helps you to quantify accuracy better than the goodness of fixed statistics. The goodness of fixed statistics, they just tell us, okay, the model is good. But how does it, so AUC, area under the curve, Kolmogorov-Smirnov statistic, Gini coefficient, even the R square, the pseudo R square in the case of logistic, okay, will tell you how good, how do you call it, the model was. But it doesn't give us, it doesn't quantify the confidence with respect to what is the percentage of accuracy. And that is why, so this is to say that if we were to bring a new data set to make the same prediction, would that model you fitted be able to correctly predict outcomes of the new data set or for a new individual? If it's able to make that prediction, then what is the degree of accuracy? And that is why splitting the data into training and testing works. So I would say that mostly just that the challenge is this. Maybe where the splitting also becomes a problem is when the event rate. So what I mean by event rate is, suppose you are trying to, let me stop sharing. Let me stop sharing. Stop sharing. Okay. So suppose, let's say, suppose your outcome variable is dead or alive. Okay. So you are predicting survival. And let's say the number of dead cases are just 6 out, whilst the number of alive cases are about, let's say, 70 or 100, meaning that if you have two categories, two or more categories, but one category have very small sample size, in that case, if you decide to split your data, it's possible you might split the data and there'll be no dead cases, or there'll be none of the smaller, because the splitting is randomly done. So it's possible you can randomly sample and the sample does not include any of the other small sample size category, just because basically the number of individuals were too small. So all of them either went into the training set or none of them went into the training set, or only a few went into the training and a few went into the testing. Okay. So in that case, I wouldn't suggest you to split your data set, especially sometimes your data set could even be 200, but your outcome is infected and uninfected. But the infected cases, let's say there are about 190 of the patients are infected and only 10 of them are uninfected. So if you decide to even split in that case, you notice that how would you distribute the 10 into the training and testing? And because this is randomly done, so it's possible when you do the random selection, all the 10 will go into the training. And in that case, you can't make predictions. I mean, you will not be able to, even the confusion matrix, okay, you'll not be able to get a better, you will not be able to do that, right? So it just, the little advice is that when the sample size is too small to make splitting possible, or one of the categories of the outcome is too small, then in that case, splitting the data is not necessary. So in that case, there's no need to quantify accuracy, but you can still assess the goodness of it using the R square, the area under the curve, the Gini coefficient, and then the Comingos-Smirnov. Each of them, any value above 0.5, between 0.5 and 1 is good enough. But the closer it is to 1, the better. Have I answered your question, please?
Yeah, thank you. Just shortly, okay. Is it advisable to do CFA before doing a regression? That is not a SEM, but then just CFA with a regression.
Okay, so basically, for those who don't know, CFA is confirmatory factor analysis. So mostly factor analysis are employed when in the kind of analysis you are doing, you have latent variables, meaning variables you cannot directly observe. And then at the end of the day, you've quantified that with some scale of measurement and those kind of things. And you are also interested in exploring like complex associations. Remember the logistic regression we just did? It's just one-dimensional association of the predictors on the outcome. You notice that we didn't explore moderation effect, mediation effect. We are not interested in that. So what confirmatory factor analysis does is that before you do confirmatory factor analysis, you have to think about the structure of your of the association you're looking at. That is, in terms of structural equation modeling, you should have a fair idea about the conceptual framework and all the kind of paths, regression paths, or all the kind of associations you are investigating at the same time simultaneously. Okay, so that is why if you're not doing structural equation modeling, then confirmatory factor analysis is not important. Confirmatory factor analysis is when you're doing structural equation modeling, it combines confirmatory factor analysis with path analysis. By path analysis means regression. Each path in the conceptual framework is like a regression. So you only think about confirmatory factor analysis. So it's more like, okay, you have a structural equation model. This is the structure or the conceptual framework. And you want to confirm whether this structure should hold or not. And so you are employing the CFA in a way to what? Take away, in a way to identify which paths are relevant and which ones are not, and so on and so forth. And then for exploratory factor analysis, this is just to say you don't know the structure of the conceptual framework. You now want to develop the structure from scratch. In that case, the best thing to do is to couple hierarchical regression with moderation and mediation analysis. And by hierarchical regression, let's say you have 3 predictors and you wanted to see how these 3 predictors predict the outcome, but you believe that one of the predictors could be a moderator or mediator. So in that case, instead of putting all the predictors in the model at the same time, you decide to put the model one at a time. So you put the first predictor into the model, and then you run the model. And then you check whether it was significant or not. But imagine when you were adding the 3rd variable, and the previous variable was not significant, but adding the 3rd variable made it significant. Then it means that 3rd variable is a potential mediator. So in that case, you would want to now do a proper mediation analysis to confirm whether it was a significant mediator. And once you use that, that is what we mean by you are doing some exploratory analysis. Okay, but by factor analysis too, sometimes the variables are too many and you don't want to use all the variables. Okay, especially when the variables are made up of categorical variables. If the variables are numeric, you use principal component analysis. If the variables are categorical, you use confirmatory factor. You use factor analysis. Okay, so factor analysis is also a data dimension technique. But from confirmatory factor analysis, you are using it if you want to confirm the structure or the conceptual framework you have defined ahead of time, either based on literature or based on your own hypothesis, what you believe, your research questions believe that that's what you're hoping to see. Then you now decide to confirm that prior to doing structural equation modeling. So it means so it meant that use structural equation modeling because indirectly it's employing confirmatory factor analysis and path analysis at the same time. Yeah. So I don't know whether I've answered your question.
Yeah, but then I think I'll follow up later with this. Thank you.
All right. No worries. Okay. Osman. Yeah, the videos will be recorded and it will be placed on the YouTube channel. So someone was asking please the recorded video. Yeah, the recorded video will be on my YouTube channel. So once you go to like my YouTube channel, if you want to access it, I think if you just go to YouTube and you type my name, you get access to that. And then I'll certainly give the codes, the R codes we've used for this class to Francis, the organizer, and then you can request for it from him as well, or you can also request for it from me when you are sending me the email to be added to the Piazza, so that once you are added on Piazza, you not only get access to this course, but you'll be able to get access to all the courses on my YouTube channel. Okay, I could just send the course for this one, but if you want to get access to all the courses on my YouTube channel when you are watching it and practicing, then you send me an email and tell me that you want me to add it to the Piazza platform, and then I'll send an automated email. It's quite straightforward for you to enroll yourself on it for free without any price. Okay. All right, Osman.
Okay, thank you very much, sir. Yes, my question is, I was a bit confused when we were assigning some of the variables as factors
Okay.
for the analysis. So I was a bit
Okay,
confused.
so basically, when you are importing data into R, most of the time, when you have categorical variables, we tend to use dummy variables, right? Even if you are using Stata or any of the softwares, SPSS, if the variable is gender, you say male is 1, female is 2, right? And when you go to SPSS or Stata or whichever software, you tell that when you see 1 means how do you call it? Males, and 2 means female, and so on and so forth, right? That's mostly what you do. Okay, so someone was asking for my email. Okay, so to everyone, I think I showed how my email could be gotten. So I have 2 emails. Osman, I'll attend to you shortly. So I have 2 emails. One is my Gmail, which I've sent on the chat, and then my Oxford University email to is I've also sent that on in the chat. Okay, so sorry for the Oxford University email, Clement should be a small letter. Everything is in a small letters. Okay, so fine. So that's my email. Okay, so I specified it. Okay, so Osman, yeah. So when you import data, whether you use dummy variable or you indirectly you test it or you directly type it as a male, female, like in letters. When you import it into R, when it was typed as letters, R will treat that particular variable as a character. Character is a type of factor variable, okay, but it's not factor. Character, it means that it's like just written letters. And then if you dummy coded it as 0 and 1, R will see it as numeric until you tell R that this is not numeric. It should be a categorical variable. So the best way you can declare a variable as categorical is to declare it as a factor. And in R, factor basically means that you are declaring that variable as a categorical variable. Even if it's character you could have still done some analysis with it, but not every function works with character structures. So sometimes converting the character, just saying as dot factor, it's just a way of declaring that variable as what? As a categorical variable in R. If it's a character variable, like you type in letters, male, female, R will still see it as categorical. But if you decide to determine the levels of the categories, R will return it I'll return it as null or empty. Empty now in this case, it means that it's not recognizing the categories. So if you want R to recognize the categories, you should now declare it as a factor. So the ask.factor is a way of imposing it as a factor. Okay. And if you go and watch the first YouTube video, for instance, you learn how if you dummy coded your variable 0, 1s, 1, 2, 3, or whatever, how you declare if 1 is this, 2 is that, 3 is that. If it was a continuous variable like age, and you want to say that you want to have 3 categories, anytime it's less than 18, between 18 and this, greater than that, how to do that in R, everything is, yeah. So factor, declaring it as factor also helps you to be able to use my function, the one that I use to summarize the data, right? If you remember, I created my own function to summarize data. If it is categorical, it summarizes the percentages with pie chart. If it is numeric, mean, standard deviation, median, interquartile range, and with histogram if you want that. So, all right. Any more questions? Okay, Eric. Yeah, Eric. Eric, you can go ahead.
Hello.
Yeah, go ahead.
Yeah, thank you so much for the presentation. It was really insightful. What I want to know is that cross-validation or lasso regression are popularly known as machine learning algorithms or models, which
Wait, before you continue. Usually I want to correct the question first before you put it well. So lasso regression is not machine learning. Okay, I just want everyone to understand it is not machine learning. Okay, it's a classical method. The only difference, just think about it this way. If we are doing the classical, let's say OLS regression, when there are multicollinearity, what happens is that some of the regression coefficients you get error message like the model failed to converge because there were multicollinearity, and because of that multicollinearity, there's a particular formula or a particular expression in the formula where you need to find inverse of matrices. But matrix inverse can only be found if the determinant of the matrix is not 0. Okay, so it means a matrix is only invertible if the determinant of the matrix is not 0. But when there's multicollinearity, it causes some of those two variables that are collinear with each other to be linearly dependent. And when it happens that way, it makes the matrix to be low rank. By low rank means that finding the determinant to be 0. And at the end of the day, finding the inverse of the matrix will not be possible. And the model will not bring any coefficient. And that also means that it will say the model failed to converge. Now, what the lasso rich and elastic net regularization do is that it adds a small constant to the part where you are trying to find the inverse of the matrix, some inverse of the matrix, where you wouldn't have been able to evaluate. It is adding some small constant in such a way that you'll be able to evaluate them whilst accounting for the effect of multicollinearity. All right, so that is basically what it does. So it has nothing to do with machine learning. It's not applying any machine learning principle. Are we okay? So the machine learning techniques are the classification tree, gradient boosting machines, support better machines, and random forest, and so on and so forth. Those are the neural networks. I mean, yeah, those are the yeah.
Thank you for that. But
Okay.
to proceed with the question,
Okay.
the ideal thing is that you have more variable than the observation for efficiency to be achieved as far as the use of these regularizations. But we're using 500 observation as against 11 variables. Although the post or the robustness checks you did for the accuracy and all shows that yes, both the training and the testing, the accuracy is high as somewhere 98%. Well, we know that those models functions very well when the variables are more than the observation.
Oh no. Let me come in. So you've brought something important, which let me just. So as we talked about, multicollinearity is when there's high correlation among the predictors. There's also something called supercollinearity. Supercollinearity happens when the number of predictors are more than your sample size. When the number of predictors are more than the sample size. But lasso and these penalized regression are able to still work in that instance. So that is the beauty and advantage of those methods. So it doesn't mean that it is only when there's supercollinearity, where the number of predictors outweighs the number of the sample size. That is the only instance these methods are used, not at all. So these methods are able to deal with both multicollinearity and supercollinearity, as well as taking away less influential variables, right? From there. So it meant, maybe the way I would ask this question is, if the number of predictors are too few, let's say just 3, 2, or probably 5, or just 3, I don't see why I would need to use lasso, okay? Because in that case, I can descriptively check, I can manually check whether, if I include all the 3 variables, or I include just 2, which one is the best based on the AIC. I can manually do that, okay? And you get what I mean? I can manually do that. But when there are a lot of predictors, let's say sometimes the predictors, especially those who work on immunological data from proteomics or sequence data and those kind of things, sometimes the number of predictors they are using, even if immunological samples, baseline immunological samples, can sometimes be about 50 to 100 variables. And when it happens that way, and there are high correlation among them, then using the lasso would help you to identify which subsets you should consider. So you get what I mean, whilst taking into account everything. So I would say that to use lasso is a variable reduction technique. So there should be a lot of variables in order to know the subset. But if the variable is just 3 or 2, then there's no need to use lasso. It doesn't make sense. Okay, because you get what I mean. It's just like doing principal component analysis, which is used for data reduction. And you can use principal component analysis for different purposes, even for clustering. We have clustering analysis, but you can use it to infer clusters. And you can also use it to identify less influential variables. But the most important thing is it's used to reduce the dimension of the data. So if I should use, let's say, how do you call it? What's the point I'm trying to make? What was I saying? Anyway, so just to say that, I mean, I've forgotten what I was trying to say. But the point is that supercollinearity occurs when there are more predictors than the number, the sample size. Unfortunately, that was not even the case in our case. But even in such cases, the penalized methods, lasso, works well as well. So that is just to say that in such instances, the stepwise regression will still be problematic. And in such instances, you might get issues of model divergence, where model fail to converge, and so on and so forth. Are we okay?
Thank you so much.
No worries. Okay, so someone is asking a question: what is homoscedasticity? Okay, so please, in terms of homoscedasticity, remember that that is not a problem when we are dealing with logistic regression. Okay, but mostly, let's say when you are doing classical regression where the dependent variable is continuous, okay, what we are saying is that the residuals, okay, there should be constant variance. So that constant variance assumption, we have graphical ways to investigate it, and we have inferential ways to assess whether the residuals were homoscedastic or not. Okay, so homoscedasticity does not apply to logistic, because logistic is more of a semi-parametric model. So it meant that it's robust to certain strong parametric assumptions that a continuous outcome-based model would expect. Logistic, we don't have to worry about that. Are we okay? Yeah, because think about it. You can only find variance if the outcome is numeric. You can only find variance of a numeric variable. Now the variable is continuous. So how do you find variance of a category? Sorry, in this case, the variable is categorical, so you can't find variance of a categorical variable, right? So that's why the homoscedastic assumption does not apply in this case. It doesn't matter. But when you are doing inferential tests like ANOVA, t-test, and those things, especially for ANOVA, we expect that the variance in the outcome should not be significantly different from the other across, let's say, the comparable groups, the groups of 3 or more. So in that case, there's a particular test you can do, okay, to test for that. But I will still say that normality is more important than the constant variance assumption when you are dealing with even hypothesis testing, right? Because it looks like testing whether the data is normally distributed is often more useful than testing whether the homoscedastic assumption was met or not. All right. And remember, it's only applicable when you are dealing with continuous outcomes, okay, but not categorical outcomes. Thank you. Any more questions? Maybe I'll take 1 or 2, and then last 2, and I should end. Okay. So Emmanuel, someone is asking a question that during my undergraduate studies, my supervisor told me one way of checking multiple linearity is variance inflation factor VRF, and by finding the average of these is greater than 1, then there's okay. So there are two ways of checking multicollinearity for each of the variables. Okay, but so it meant if you fit the regression model and you even type VIF around the model, you'll be able to know the individual contribution of collinearity to data. Okay, and when you fit a regression model and the variance inflation factor, and there's something called tolerance. Tolerance is the inverse of the variance inflation factor. You can use that to assess if the full model has problems of multicollinearity, or you can also use that to check each of the variables that is contributing to multicollinearity. If you are using lasso regression, you don't need to worry about that. If you are using the lasso elastic net for future selection, you don't need to worry about that. But if you want to know which variables are contributing to multicollinearity, even doing a simple correlation matrix plot will give you a fair idea, especially what we did, or calculating the variance inflation factor or tolerance for each variable will help you to know the marginal contribution of each predictor to that. And instances where you notice that, so it means you can have individual variance inflation factor for each predictor, and you can have the overall model variance inflation factor after adjusting for all the other variables. Okay, and anytime the variance inflation factor is maybe above, let's say 4, 5, 6 in magnitude, that tells you that the model has high effect of multicollinearity, and it suggests why you need to rather consider a penalized regression rather than the unpenalized regression method. All right. So have I answered you? What's the name? Emmanuel. Okay. So someone was asking, is testing a model the same as fitting the model? No. So as I said, in terms of the model cross-validation, by testing model means that you have fitted the model, right? And at the end of the day, the model can also make predictions. So if I have a new data set where I knew the outcome variable, whether the weapon was a knife or a spear, for a particular individual, okay, I knew the weapon which was used. And at the end of the day, I want to now use the model that I have fitted to be able to check if I can make a correct classification or a correct prediction. And the proportion of times I'm able to make those predictions to be true is what quantifies the overall accuracy. At that instant, it has nothing to do with simulation. Okay, so simulation, if you look at how I generated this data, I did simulations. Okay, so that's one example. So simulation doesn't apply to cross-validation. Cross-validation is like the prediction, you don't call the prediction as simulation. You saw the exact formula that we use for making a prediction. So if you want to call it simulation, maybe you want to say that you are trying to use a synonym that you are simulating the outcome, but it doesn't still make sense. The word is you are predicting the outcome. Okay, so you are not simulating the outcome, you are predicting the outcome. Okay, but when you are simulating data, it's just like simulating means you are creating an artificial data set. At this stage, we are not creating any artificial data set. We are rather making predictions of the outcome, and we are comparing that with the true values in the testing data set to check whether the proportion of times they agreed or not. All right, thank you. Maybe last question and I should end. Yeah, Osman, because we spent a lot of time. You spent
Okay,
like close. Okay.
thank you
Yeah.
very much, Doc.
No worries.
Doc, please, I'm trying to analyze my data. That is one way ANOVA. And I've been able to fit a model for the one-way ANOVA analysis, but I'm having challenge with the multiple mean comparison. Anytime I
Wait, so
fit it, doesn't take.
also anytime you fit, what happens?
Well, the last time I fit, I succeeded all right, but it didn't display any results to me. They told me that something like none is numeric. That's what I saw.
Which software were
Using
you?
the arrow console.
Okay, that's fine. So I think all you need to do is just go to Google, Google, and type how to do ANOVA in R. But remember this. Remember ANOVA and type ANOVA with multiple comparison. You can even do it in ChatGPT. Just go to ChatGPT and type how to perform ANOVA analysis with multiple comparison in R, and that will do it for you. Even if you want to visualize the pairwise differences, you can tell ChatGPT to do that for you. But the take-home message is this: your dependent variable has to be numeric. So if we're getting errors, it's probably when you imported the data, it didn't see your dependent variable as numeric. So the best thing you can do is that you can extract the dependent variable and equate it to as dot numeric of that variable. Just like I was declaring some as dot factors when they were characters, I said as dot factors to impose them as numeric categorical. If it's numeric, check the class. If you check the class of that variable and it concluded it as numeric, then it was. But if it didn't conclude it as numeric, then it means that you have to impose it as numeric. Maybe after you imported it, it saw it as a character. So in that case, you get that error. And another thing is that the pairwise comparison is only used or applicable when there was significant difference. Remember that if there's no difference between any pair of the variable, then overall ANOVA will conclude that there was no significant difference. But when overall ANOVA concludes there's a significant difference, then in that case, it means at least one of the pairs were significantly different. Okay. So this is to say that if your ANOVA p-value was not significant, don't even worry about pairwise comparison. You only worry about pairwise comparison when the overall model was significant. And if you're getting errors in R for that, then it means that the dependent variable, maybe you were supposed to declare it as numeric, you forgot, or the predictors were supposed to be declared as a factor. R saw it as character, so you can impose as dot factor on the character variables, and that will also work. Are we okay?
Yes, please.
All right. So
Thank you
on
very
this note, because of time, I guess someone is asking, meaning me. Ishmael, do you want to ask your question? I couldn't get what you meant. Meaning, check your variables. I don't know. Oh, are you saying that meaning check your variables as a response to the guy? Okay, that's fine. If that's the case.
I think he was responding to Usman's question.
Okay.
Yeah. So, okay. So thank you very much, Dr. Chumasi, for your time. It has been a long day, and we appreciate your time. And also, I know you are kind of a very busy person like me. Myself, I was awake since 1 o'clock. Yeah, I was praying, and then I had to I didn't want to sleep off. So, yeah, wise for today. Tomorrow to is Sunday, I have to be in church. So I just want to say thank you very much for your time. At least you've opened our eyes a lot. All this while we've been using the R console and the R studio to do our trainings. But I think with this training, we'll shift our focus to the Julia and the Jupiter, like what you just took us through, so that at least members will appreciate R more. And I was really happy with the way you were able to touch on qualitative and quantitative, because in Ghana here, normally that's what they use when it comes to data analysis and running analysis to maybe do some publications or maybe to work on their project works and stuff. And I'm happy you were able to touch on the basics a bit, the intermediate and also the advanced level. I think as you've done that, I think they have appreciated the way the tool, the art tool is. So once again, I just want to say thank you very much for your time. And I think you've opened my eyes too as well, because normally I focus more on the quantitative, but then I don't really look at the qualitative aspect. Normally, when it comes to qualitative, I use NVivo to run my analysis and do all those stuff. But then I think from now on, I'll probably use R to do more on the when it comes to qualitative. Once again, I want to say thank you very much for joining and for taking us through. It's been 5 hours. Yeah, I think almost 5 hours. 1 minute to 5 hours presentation, and we really appreciate your time and your efforts. God bless you very much.
I would say 4 hours or 3 to 4 hours. Yeah, 4 hours or something. Yeah, that's quite intense. We started at 11.
Yeah.
So I think 3 hours.
Yeah, 3 hours. Yeah.
Okay, so please don't forget to subscribe to the YouTube channel. So please encourage them to also subscribe. That's my only motivation.
So your channels I have kept on our page, on the Ghana R page. I kept your YouTube link on the page for them to follow.
So in the chat, I think I've also pasted my YouTube channel. So please, everyone, try and subscribe and learn at your own pace. Start programming from scratch. R is the tool. And if you watch that first video, you'll notice that I have so the recording will be placed on the YouTube video as well. So please, is this Salifu? So subscribe to the YouTube channel. So once the video is placed, you get access to it. I will do some editing and cut away things that are not important, especially with the noise and other distractions, so that it will be more professional video, so you can all access it. Okay, so please don't forget to subscribe, and thank you very much myself. I'm always honored.
Very much. I think I just shared the WhatsApp link. Those who are not on the page, kindly join, and please let's do this. Let's subscribe. I also share the info.
Okay, no worries. Okay, then I'll end here.
All for joining. We are grateful. Yeah.
Bye-bye.
Bye-bye. Thank you.
Bye-bye. Mm.